We all know what this is. An atom, with a nucleus of protons and neutrons, and electrons orbiting around it. But have you ever thought about the fact that the electrons have a negative charge, and the nucleus has a positive charge? So according to the laws of classical physics, the electrons and nucleus should attract each other. This would cause the whole atom to collapse. But this doesn't happen. Heisenberg's uncertainty principle explains why. You've probably heard about Heisenberg's uncertainty principle, but you might not know what it means or how it works. The theory was developed by German physicist Werner Heisenberg in 1927. It states that we cannot measure the exact position and momentum of a particle at the same time. If we're more certain about one, say the position, we're less certain about the other, the momentum, and vice versa. What we see here is a particle with a certain xy position and a certain momentum. What Heisenberg's principle tells us, however, is that in the quantum world, we cannot give the exact position and momentum of a particle at the same time. If we try to give an approximate momentum to a particle, as we see here, let's say somewhere between 4 and 6 kilograms times meter per second, the location of the particle on the coordinate system is less certain. It could be here, but it could also be here, or here, or here, or here, or here, or here, or here. If, on the other hand, we decrease the uncertainty of its position, say it could only be here or here, then you see the momentum in red becomes less certain. Instead of being between 4 and 6, it's between 1 and 9 kilograms per meter per second. The reason we cannot measure the exact position and the momentum of a particle at the same time is because everything in the universe exists both as a wave and a particle. Objects like an eraser, a pepper, or a shell, and the particles of an atom too are all simultaneously waves and particles. We can't observe this in the world around us because the waves are so small. To illustrate this, let's take an everyday object, an eraser, with a mass of 10 grams or 1/100th of a kilogram. Let's give it a speed of 1 meter per second. Now let's put these values in an equation that gives us the wavelength. The equation is Planck's constant, represented by h, divided by momentum, or p, and this gives us the wavelength, represented by the Greek symbol lambda. Since momentum is mass times velocity, we can replace the p with m times v. Now let's plug the numbers into the equation. The mass is 1/100th of a kilogram, its velocity is 1 meter per second, Planck's constant is approximately 6.6 times 10 to the minus 34 joule seconds. After doing the calculation, we get a wavelength of 6.6 times 10 to the minus 32nd meters. This is a value that's smaller than the size of a proton, so there is no way we would be able to observe the wave nature of the eraser and has no effect on its movement. This is not the case on the quantum level, because the waves are large enough relative to a subatomic particle's size so that its wave nature does affect its movement and position. Now let's look at a subatomic particle and see what happens if we try to find its exact position. We can do this by combining lots of different waves with different momentums for any particle. The math behind this is complicated, but all we need to know is sometimes the waves cancel each other out and sometimes they reinforce each other to produce a wave packet. A particle is somewhere in this packet. If we add more and more waves, all with different momentums to the packet, we get a narrower wave spike, so we can be more certain about the particle's location, but with each added wave, we sacrifice certainty about the momentum. There is a calculation that explains this. We take the uncertainty of the particle's position, represented by delta x, and multiply it by the uncertainty of the momentum, represented by delta p. This has to be larger or equal to Planck's constant divided by 4 pi. Okay, let's use some simple numbers to show why, if we increase the uncertainty of either momentum or position, we decrease the uncertainty of the other. Let's say the uncertainty of the particle's position is 2, the uncertainty of its momentum is 4. For simplicity's sake, let's say the equation gives us an answer of 8. If we decrease the uncertainty of a particle's position to 1, we need to increase the uncertainty of its momentum to 8. We can continue decreasing one and then increasing the other proportionately. This is why an uncertainty of 0, that is knowing the exact position or momentum, is impossible, as it would break the equation. It would be like getting an error symbol. That's why an atom doesn't collapse. If the electron is spun into the nucleus, we know its exact position, and that's impossible. Not just because Heisenberg's equation tells us this, but because uncertainty is a fundamental feature of the quantum world. Heisenberg's equation is just a description of this reality.